Hello everyone and welcome. My name is Reza and I'm founder of the website www.optimizationct.com. In this video, we will explore solving the linear programming model using the three different methods: the Simplex algorithm, the GAMS software, and finally an online solver provided by the website www.optimizationct.com. So go on. In this tutorial, we will first solve the linear programming model using the simplex methods step by step. Then we will solve the same model using the GAMS software and finally solve using the online solver provided by website of optimizationct.com. After solving the model using these three methods, we will compare the result. Presenting the model we will solve consists of the two variable and two constraint. We will go through the formulation step by step by simplex methods. Solving. Alright, let's start by solving this model using the simplex prime method. First, before we do anything else, we need to convert the model into the standard form. What is the standard form? The objective function need to be maximized. All constraints should be less than or equal format, and the variable must be non-negative. Since we have the inequality in this constraint, we need to introduce the stack variable to transform them into the inequality. So here we have 4x1 plus x2 plus x3 is equal to 20. This is the slack variable. For the second constraint, x1 plus 4x2 plus x4 is equal to 14. So x4 is the slack variable. We also rewrite the objective function as an equation. So it means that z minus 6x1 minus 8x2 is equal to 0. Now our model is ready to place into the simplex tableau. Okay, we change the color. It's better. Here, how we organize our table. The first column, name the basic variable. Second column, row number 0 for the objective function, and row number 1 and 2 for constraint number 1 and constraint number 2. Remaining the column coefficient of the all variable in the model. And the last column is the right-hand side of the model. To convert inequality into the equation, as we stated before, we introduce x3 and x4 as a slack variable to the model. Now let's fill out the table. A coefficient of the z. Oh, this is the z. Basic variable for the first row number 0. This is the row for objective function. The coefficient of the z in row number 0 is 1. And 0 elsewhere. So because we don't have any z for in constraint number 1 and constraint number 2. The coefficient of x1 in row number 0 is minus 6, as we write here. In constraint number 1 is 4. Here, this is 4. And in row number 2, row number 1, number 2 is equal to 1. Okay. x2. The coefficient of the x2 in row number 0 is minus 8. In constraint number 1 is 1 and constraint number 2 is 4. The slack variable x3 and x4 do not appear in the objective function, so their coefficients are 0. In constraint number x3, in row number 1 is 0, is 1, and in row number 2 is 0. x4 in row number 1 is 0, and in row number 2 is 1. The right-hand side of the model 0, 4 equation of objective function, and 20 here. This is 0, 20, and 14. And this is x3 and x4, the basic variable for the first table of the simplex. Let's begin with the pivoting step. We need to choose the entering variable. To decide which variable enter the basis, we look at row number 0, so without it. If all non-basic variables here, x1 and x2 coefficient are non-negative, we have reached optimality and we can stop. But in this table, the coefficient of the x1 is -6 and the coefficient of the x2 is -8, meaning we are not yet at optimality. Now we recommend choosing the most negative coefficient, since this generally leads to the faster solution. Here x2, the coefficient of the x2 is -8, is the smallest, so we choose x2 to enter here. x2 is enter. Now we need to choose the leaving the variable. To determine which variable exists, we use the ratio test, which only apply for the positive number in the pivot column. This is the pivot column. For row number 1, 20 divided by 1 is 20. And for row number 2, 40 divided by 4 is equal to 10. The other column is red. Okay. The row with the smallest ratio determines the leaving the variable, which is in this case x4. So now this is x4, exit the basis. So x2 enter and x4 exits to the basis. Now we swamp x2 into the basis and x2 out. So here z, x3 and x2. We need to adjust the table. The pivot element here are 4. This is the pivot element. The pivot element here is 4. To make it 1, divided row number 2 by 4. So the pivot become 1. Use the row operation to eliminate x2 from other row. So it means this is row number 0, 1, 2, 0, 1 divided by 4, 1, 0, 1 divided by 4, and 10. Okay, so use the row operation to eliminate x2 from the other row. So it means we multiply by row number 2 by minus here. Here we need that order. Okay, we need to divide row number 2 by minus 0.25 and add to row number 1. So as a result, this is 0. 1 divided by minus 0.25 plus 4 would be 3.75. 4 divided by minus 0.24 plus 1 is equal to 0. 0 divide 0 multiplied by minus 0.25 and plus 1 is 1. This is minus as well. And here 40 multiplied by minus 0.25 and plus 20 would be 10. As a result, the coefficient of the x2 in row number 1 would be 0. And we multiply row number 2 by 2 and add to row number 0. So as a result, 1 divided 1 multiplied by 2 and plus by minus 6 would be minus 4. This is 0, this is 0, this is 2, and 40 times by 2 and plus 0 would be 8. So you can see that x2 would be 1 in row number 2 and the other would be 0. Let's check the optimality again. Now we check row number 0. All values are non-negative. The answer would be no, because we have here the coefficient of the x1 is still minus 4, meaning we need another iteration. Okay. Now x1 enter the basis because the coefficient of the x1 is minus. Now x1 enter the basis and we repeat the ratio test. The ratio test 10 divided by 3.75 is 2.6 about, and 10 divided by 1/4 would be 14. As a result, the smallest value is 2.6 in row 1. So x3 exit and x1 enter. So what is the pivot number? Would be here. Again, we update the table. Make the pivot element in row number 1 divided by 3.75. So z x1 x2 0 1 2 1 0 0. Okay, we divide row number 1 by 3.75. So 1 0 4/15 minus 1/15 and 8/3. In order to make 0 the coefficient of the x1 in row number 0 and row number 2, we need the operation we stated before. So it means Okay, some dirty word, but it doesn't matter. I should tell you. Okay, we multiply row number 1 by 4 divided 3. Okay, we multiply row number 1 by this number and add to row number 0. And for make 1 over 4 to 0, we need to multiply row number 2 by 1. This dirty number. So as a result, the table for the final step would be here. So you can see that 0, 16 over 15, 26 over 15. What is the right hand side is about 90.6. The row number 2 minus 1 over 15, 1 over 16, and 9.33. Now, looking at row number 0, you can see that all values are non-negative. It means that we found the optimal solution. What is the optimal solution? Optimal solution is x1 is equal to 8 over 3 and x2, sorry. Okay. x2 is equal to 9.33, and objective function, what is the objective function, is 19.6. Also x3 and x4, because our non-basic, is equal to 0. That's all. The Simplex method successfully found the best solution for our linear problem. Now let's solve this model using the GAMS. In GAMS, we define the index I because we have two variables. So, okay, because we have two variables, I is equal to I and 1 and 2. We have two variables, x1 and x2, as a decision variable. X1 and x2 is non-negative. So we just write the positive variable. It means the non-negative. But because z, or objective function, is free in sign, so we just write the variable. We have one objective function and two constraints. Obj cons 1, cons 2 in the section of the equation. Here, in the section of the equation, we define the objective function is equal to 6x1 plus 8x2. 4x1 plus x2 is less than 20, and x1 plus 4x2 is less than 14. As we stated before in the earlier video, we have three signs in GAMS: equal, L equal is less than, equal E equal is equal, and equal G equal is greater than. We use the solve command to solve this model using the NLP solver in the maximization form of the objective function. We use the display command to show the objective function as x dot L, or level of the optimal solution for x. So what happened in GAMS? Here, this is the GAMS. just prefer before, and this is the new project, and copy and paste and just press the red arrow. As you can see here, the x is 2.667 and x2 is 9.333, and objective function is 9.6, as we found in the simplex methods here. Okay. Next, let's use the online solver in the website of the www.optimizationct.com to solve our model. In order to do this, we should do something before. This is the model we have. Okay. Sorry. Okay. Okay. In order to use the online solver of the website of the www.optimizationct.com, here we navigate this website and online solver, prime and simplex methods. So we have N, M, E, P, S, and A. What is these input parameters? So we have here okay, right hand side, okay, x1, x2, x3, x4. We need add to x3 and x4 to make this equation to equality. So right hand side of the objective function is 0, 6. The coefficient of the x1 in objective function, the coefficient of the x2 in objective function is 8. The coefficient of x3 in objective function is 0. The coefficient of the x4 in objective function is 0. Right hand side of the first constraint is 20. The coefficient of the x1 is objective function in first constraint is 4. The coefficient of the x2 in first constraint is 1. The coefficient of the x3 in first constraint is 1 because we need x3, x4. Okay, 0, 14, as we stated before, 1, 4, 0, 1. So what is the A or A matrix? This is the A matrix, the coefficient of the model. So n is the number of variable is 4, and m is the number of constraint is 2. EPS, the precision of the algorithm is 0, 0, 0. So let's move on to the website. Okay, we have the coefficient entries here. Okay, 4, 2, sorry, 2. 0.001, and this is, and just press the run, and you can see that the x1 is 2.6 and x2 is 9.33, and objective function, we have the optimal solution here, and objective function is 90.66, as you can see here. In this example, we solved the model using the simplex methods, GAMS, and online solver. An interesting question remains. In the simplex method, we initially choose x2 as the integer variable. However, we could also use x1 because its coefficients also are non-negative, or also negative, sorry. So here, we can also use x1 as an integer variable. What would happen if we had chosen x1 instead? Would it take more operation to reach to optimal solution? Leave a comment answering this question, and I will discuss it in the future video. Thank you so much for watching us. If you have any question or need help solving a model, feel free to contact us by email or filling the contact form from our website, www.optimizationct.com. Do not forget to subscribe our YouTube channels to stay updated with our video. Thank you so much and goodbye.